it's been so awesome. We've had some incredible and empowering talks today, and we're continuing with Smiti Sharma, Senior Director of System Engineering at DataStax. Smiti is a passionate technologist, a leader with 20 years of experience in global systems engineering and IT consulting strategy. She leads a team of engineers at DataStax who work to architect complex solutions for large enterprises. Today, she's here to discuss how companies are using machine learning and AI embedded in transactional systems that deliver real-time insights to their customers. And don't forget to stop by DataStax booth in the Expo Lounge and learn more about them and continue the conversation with Smiti after. Over to you, Smiti.
Hi, everyone. I'm Smiti Sharma. I work at DataStax, and here I lead a team of solution engineers and systems engineers who work with our customers to design applications and their critical business function databases. Personally, I've been in the space of databases and analytics for almost 20 years. I've worked at Oracle, Amazon, at AWS, and also at Pivotal, where we worked on Greenplum, which is an analytics database. Today, I'll be talking to you about the convergence of data governance, and AI/ML, and I'm super excited to share what some of our customers at DataStax have done in the world of analytics. So with that, let me share what we're going to cover today, and hopefully we'll have some time for questions later on. I'll introduce you to a few concepts around machine learning and analytics, as well as data governance. We'll talk about a use case that one of our customers in financial verticals has effectively implemented in their productions. And we'll also talk about the intersection point of AI/ML with data governance. So in general, I would say these four things are the tenets or the design principles, whether you're building a net new application or you are migrating from a legacy platform into a cloud-native platform, per se. You could choose to go into a hybrid cloud infrastructure, and that could be a combination of both private and public. You could also choose to do multi-public cloud infrastructure deployment. On top of that infrastructure as a service, if you will, you would have a data management layer, which is what your persistent store is, both for transactional and analytics. But we recommend that be rooted in a foundational data management strategy. The other hallmark of that platform has to be that it is self-service, as well as machine capable and massively scalable. And to be able to build any software application on top of that is where you would need a very developer-friendly agile toolkit. And when we talk about databases, this is, like I mentioned before, both transactional and analytical databases. And in both of them, there are situations where you want to be able to handle real-time queries, as well as real-time data sets, as well as be able to massively scale. And particularly in what I'll talk about in the next few slides is for transactional applications, when you want to be able to distribute that data globally and scale massively. It becomes very important that the architecture allows you to do that, and it is very end-to-end configurable. From a data management strategy, which is a subject in and of itself, but I would just sort of premise by saying that there are some absolute principles within the data management strategy that are the hallmarks of a very good design. And that is things around whether the business metadata, as well as the technical metadata against that data, has been defined, whether it's at source or further down the stream, which in many cases becomes super challenging. So it's best to define that as the data gets captured. And we'll talk about that in a little bit. As well as around data, what are the aspects that define it specific to security? So in other words, is your data such that it is sensitive, it has personal information, and therefore should be labeled as such, and therefore stored as such? And from that come technical requirements like encryption and obfuscation and things of that nature. The other aspects around data management is the lineage of the data, as well as audit, that allows you to see who has actually accessed the data. So that's more of a historical analysis. And certainly authorization and authentication are the other elements from a technical perspective. Most generally, what we've seen is organizations have a data management policy, a framework, and sometimes a data council to define all these parameters. So what does DataStax do? So this was a company that was founded in 2010, and it was built to support and enable enterprise-level Apache Cassandra. Apache Cassandra is a NoSQL database, and it came to be around 2008. It was inspired by the paper that was written by Google, which was around Bigtable, and the other paper that was written around 2007 by Amazon on DynamoDB, or Dynamo as such. But essentially, Cassandra is a NoSQL database, and almost 92% of Fortune 100 companies today run Apache Cassandra in some form and fashion in their production systems. And then when we look at the enterprise adoption of Apache Cassandra via DataStax, almost 40%, excuse me, and more of Fortune 100 companies run DataStax at enterprise, as well as other components of DataStax. So we believe that Cassandra is one of the best NoSQL databases that is available in the market for a variety of different reasons, 3 of which are absolutely critical for any transactional platform, as well as analytics platform, depending on the use case. It provides a 100% uptime, so zero downtime, zero lock-in, specifically when you are running Cassandra in the cloud in the form of software database as a service that we'll talk about in a little bit. This is where you can choose to run Cassandra either in Amazon or AWS or Azure or GCP. So it's very cloud native, it's migratable and portable. And then finally, it has global scale. And what we mean by that is you could have a Cassandra cluster which has your data, the customer data running on it in 3 different continents. So it's globally scalable. When one region goes down, or a set of nodes within one region goes down, the other 2 or 3 regions will actually be able to service the requests from your clients. So you're 100% up all the time, and therefore also have global scale with that architecture. So we believe Cassandra is the best NoSQL database of choice for a variety of different reasons, but 3 of which are absolutely critical for majority of the applications. And these are absolute hallmarks of the platform. The first is 100% uptime, which means there is no downtime and you're active everywhere. You scale linearly, therefore, and it is also an architecture that does not have a master. So every node within the Cassandra cluster is equal. The second element is the zero lock-in, and this is when you're running in a cloud-native platform, whether it's in AWS, Azure, or GCP, you could port your database cluster across any of these public cloud vendors. So there is no lock-in on any given platform. And you could also run in a hybrid cloud environment where you have a few nodes of Cassandra cluster running on premises and the remainder in any public cloud. So it has a very flexible architecture in that regard. And certainly global scale. You could run in 3 or 4 different continents with clusters distributed across all these. That also allows for 100% uptime as well as linear scale, and allows servicing of the clients from different regions at a faster speed. And if you're actually using a website or a smartphone today, you're at some point touching a Cassandra backend anyway. So this is something to be quite proud about in the way the platform has been built. Let's spend a few minutes on machine learning. Fundamentally, this is a process where you're processing a large amount of raw data. You use mathematical algorithms to make better decisions on top of the data that is provided to you. And the more data you have, the better the decisions. So simply put, this is massive amounts of data on which you're running algorithms to receive outcomes. There are 3 primary different kinds of machine learning categories, the 2 of which we'll focus on today: supervised learning and unsupervised learning. Really, the way to differentiate between the two is when the supervised learning is using essentially labeled data sets. So you already know what the data is by way of metadata. And the two primary ways within this category to achieve outcomes or to have any kind of a prediction is classification and regression. An example would be fraud detection, which we will drill a little bit deeper into later today. The other category is unsupervised learning, and this is basically when the data is not exactly labeled. So the algorithms will allow the model to learn from itself and learn from the data that it collects, and also in the process label the data as it proceeds and ingests and processes more and more data. So this is a very high level view of what machine learning is. And really, when you look at the transactional platform and the analytical platform, which, for those, the truest people, many a times that is 100% segregated. But there are also times when the two are converging extensively, especially in the kind of the use case that you're running it at, right? So the key is all the time delivering the right data to the right place at the right time so that you can support the right experiences or use cases, all of that bundled with the right governance around that data. So that's sort of the premise of what analytics in general allows you to do with the data you collect, right? So let's see that in action a little bit. So in the financial industry, this particular page talks about the various aspects of tech implementations, whether it's, how do you process retail cards from core banking to security, GDPR. So all of these are aspects of IT within financial industry. The ones which are in red is where you would use some form and fashion of machine learning and analytics to derive outcomes. Let's focus on fraud a little bit. Two of our customers, ACI and Bank of America, use the platform extensively to actually specifically do fraud detection in credit card payments. And if we look at closely how this transaction comes to be, let's say if you have a person who is making a credit card purchase online, whether it's using a mobile or a browser on your laptop, it doesn't really matter. That's the device though, but each of them will have a device ID allocated to them. And there is a person whose username, hopefully you would know because you're logging in through a portal. You could also have IoT devices or in general processes that transact and use your credit card. An example is, let's say your Hulu subscription or your magazine subscription automatically 25th of every month goes and charges your credit card. Those transactions, after a bunch of different hoops and going through various endpoints, various gateways, will actually hit the database or a data store. And that data store looks at other trained embedded models in order to make a determination if that particular transaction is legitimate or is fraudulent. And that has to happen in milliseconds, right? Once that's done, then the order is acknowledged back to the person, or in case of devices, it's actually rejected flat out, right? But what goes on behind the scenes is a combination of both data governance as well as analytics. So for instance, the trained models already have this information around the data called labeled, or in other words, they use labeled data sets. So they would have things like credit card number, the name of the person, the device ID, a location, sometimes geographical, depending on what you have enabled in your platform. They would also have the name of the person and a lot of different things. The governance that goes around storing this data is of imperative importance. Things like protecting the credit card information because of the PCI rules and protecting personal information because of PII rules. And that is where the governance integrates. And this is all the way from transactional or the genesis of your data up to the analytics system. But then in the background, these trained models or these models which are getting trained would actually look at all these variables from the point of view of, do they all collectively make a pattern, and do they all collectively make a sense as the pattern develops over a long period of time? So they're looking at things like the frequency of charge, what is the amount of transactions, which is an average for a given person, is the device ID, which is likely the residential IP address / device ID, accurate one, and is there a consistency in that? So all those things are looked into to determine if that transaction is accurate. And then the fraud would be triggered if there is any unusual activity in any of these. So that's sort of the general schematic, logical view of credit card transactions. And it's very important that while these transactions are happening, there be as many low false positives as possible, so that the confidence level of the person using the credit card stays up, and so for the merchants as well. Now, granted, there are a number of different effective fraud tools, and we are just talking about a sliver of them. When you could do the fraud detection by doing, device fingerprinting or card verification, or even looking at email verification, two-factor phone authentication, and a number of different things. And the industry has used a combination of all of these on an ongoing basis. But I would say that a lot of what is built is dependent on these four basic pillars. The first one, I would start from the bottom right, is the distribution of data. As you look for patterns, the more the data, the better to achieve low false positives. But then the more the data, the longer it would take to process it. And that's where the speed of transactions come in. So at that point, the decision from a technical perspective you want to make is, do you take only lesser and lesser amount of data? So instead of taking 10 years worth of data to develop your pattern, do you take 5 years or do you take 3 years? But then that's going to incorporate some error in your model. In order to avoid that, you want to be able to scale the database or the system as much as possible. And that's where the scalability comes in. And all of these three elements or dimensions are going to have an impact on the accuracy of your algorithms. So it's a fine balance that is periodically addressed from an IT architecture perspective as time goes by. So this diagram here is sort of under the covers of what we just discussed to be what we just discussed as a financial transaction. So, and to quickly go through this, if you go from the left to the right of this diagram, as you get streaming raw transactions, there are two paths to that transaction, right? There is the real-time fraud detection path, where you do some bit of feature engineering, you identify what those elements or factors are that are going to be very important in detecting fraud. And then on the top, the bifurcation of that same data goes into improving the model that you have already hopefully built over time. And that also actually goes into your data catalog. That's where again, data governance, data integration with data management comes in. So this diagram here talks about the details of the fraudulent transaction that we covered just a few minutes back. If you go from left to right on this diagram, as the streaming raw transactions come in, there will be two paths for that data to take. One is the real-time fraud detection path, which is actually going into your transactional system. And then the other one is going into the offline model training. That model training system could arguably be an analytic system, and in some outlier cases, depending on the volume of data, could also be your transactional system. Right, but the logical path will be such that you take the path which is for model training, go into developing that model, improving that pattern analysis, and do that feature engineering, as well as sort of enrich your data catalog and data management space. And then the second path, which is the real-time fraud detection path, is where the sub-millisecond processing of that feature tuple happens and fraud gets detected. And then finally, the output to the end user goes in. So this is kind of what goes on under the covers, certainly very simplistic representation of a real-time and analytics near source. Here's another depiction of where does data management come into picture, especially when talking about financial transactions or low latency, high performance transactions. Again, from left to right, as you ingest the data, you want to be able to identify what data it is, meaning is it coming from a device? Is it human generated? Is it an IoT data? So a little bit of analysis as to what the genesis is of that data will help determine the lineage of the data, which is one of the features within the data management spectrum. As the data goes into the data store, you want to be able to set it or sort of ingest it into a data model. Again, data model should capture a combination of business and technical metadata around the data that just was persisted. The quality of the data should be determined here. I've seen many of my customers, many of our DataStax customers actually enrich the data as the data gets ingested and improve the quality of the data, which could then be used to do a combination of access control, security control, also determine what the governance would go in terms of what compliance framework it has to adhere to, for instance, HIPAA, PCI, PII, and so on and so forth. So this is where is the intersection point of data management. And if you notice, this is being done not downstream in an analytic engine, but it's actually being done in the transactional platform. So this is ACI Universal Payments, which is DataStax customer and have been a long-time customers. There are a few talks that you can go find online, and they do a really good job of describing how they've been able to build an architecture which is being able to identify credit card fraud for both merchants and payers in microseconds and milliseconds. I think it's a very powerful read, and I encourage you to look at it. So in summary, this is what the open data stack for modern data apps looks like. I think in this day and age of having to consume large volumes of data at a high velocity and in a continuous streaming fashion, we want to be able to build applications from the point of view of being able to service customers with the right data at the right time with the right experiences. So this platform and stack will allow you to do that in a very effective fashion so that you can innovate in your businesses. So just to kind of walk through this real quick, from the bottom of the diagram going upwards, you could choose any public or private cloud platform. The DataStax stack is actually built on Kubernetes, which allows you to develop, which allows you to spin containers and deploy applications, as well as port them very quickly. And that is sort of the core and the basis of our portability feature. Then the Cassandra database is enwrapped within the Astra DB, which is sitting on top of Kubernetes, along with the streaming engine. And then we expose all the data APIs, whether it be GraphQL or document or REST APIs, to be able to do development very quickly and in a very agile fashion and build all those analytical algorithms that would be used for various use cases in various domains. So really, all this is possible so that you could work on massive amounts of data at a global scale with 100% uptime and with little code. And we believe that this platform is 100% developer ready and is very easy to use. So in summary, we covered some tenets and some features around machine learning and data governance. We looked at how contextual and timely data can provide a high value to your businesses and allows you to innovate. We also talked about the design considerations for transforming applications, which would be key for new applications as well as transforming legacy applications. And this is a combination of building all the way from infrastructure to your developer and what features are needed for them. And that's where architecture and requirements sort of intersect. And we also talked about the fraud detection as a key use case. So I invite you to look at the DataStax website, look at the events, and learn a little bit more about Astra. Thank you.